Hello, everyone. So I'm going to talk about the TypTop systems. It's a joint work with my co-authors from Cornell, Royal Holloway, and Technion. So I'll begin with how normal password checkers work. So when a user tries to log in with a password, the server applies a slow cryptographic hash function on the password and checks the output of the hash value with a stored hash digest that was computed during registration. If the strict equality check passes, the user is allowed to log in, otherwise not. And users make mistake. So if a user make a small mistake, such as like accidentally capitalize the first character of the password, the output of the hash value will be completely different and the login will be rejected. This is very annoying and counterproductive. So we looked into this at length in a paper published in last year, Oakland. We introduced a notion of typo-tolerant password checking, where the idea is that a user will be able to log in not only with the registered password, but also some typos of it. The way we propose it to be done is like when we see that a user entered password is wrong, we'll apply a set of corrector functions, such as a caps lock corrector will flip the case of all the characters in the password, and then check the correction in the same way we check the submitted password. That is, you apply the slow hash function and check the output of the hash with the stored hash value. If any of these corrections passes, the user will be allowed to log in. We showed in the last paper that we can come up with 5 corrector functions that can correct 20% of all typos that users make. We went on and did a measurement study with a live Dropbox login server and showed that if we correct this 20% of typos, that will improve login by 3%. Now, a company of the size of Dropbox with hundreds of millions of users, this is a significant improvement in login. We also showed that if we choose the corrector functions carefully, there will be no degradation in security. However, this only corrects the tip of the iceberg. 80% of the typos are left uncorrected. If you want to correct typos in the same way using corrector functions, there are few limitations. The first, that every correction needs to be checked using a slow hash function. Therefore, if you want to check too many corrections, that will be very expensive. These corrector functions are chosen based on population-wide statistics. Therefore, most of the corrector functions are not useful for every user, and that's kind of wasteful correction. And finally, if we have to be very careful about what we correct, because if you correct too many of them, then that might degrade security. So this leaves us with the question that how can you correct more effective typos without degrading security? So to this, we propose a new mechanism, which we call personalized typo tolerance. The idea is we will correct only the typos that a particular user makes. Now, how do you know what typos a particular user makes? So for that, we designed TypTop. The TypTop adaptively learn what typos a user makes and then correct a frequent subset of it. We thoroughly analyze the security of TypTop and show that it's secure against online and offline attack, which I will explain in length. And then finally, we build a prototype of TypTop to render computer logins adaptively typo-tolerant. So let's say what I mean by adaptively typo-tolerant. The idea is when the server monitors the mistakes that a user makes, and if a user repeats the same mistake that he made in the past, we will let the user log in. Now, two questions arises from this model. The first one is the whole concept of adaptive typo-tolerance is predicated upon the assumption that users repeat their mistake fairly often, that it will be profitable to correct past mistakes. So we first want to see whether or not users make mistakes fairly often. And the second question is, how would the server or the password checker know at the time of login that some incorrect submission is indeed a legitimate typo and not an attacker's guess? Because we'd like to verify a legitimate typo by checking, for example, like edit distance between the submitted password and the original registered password. But during login, the registered password is not available in the plaintext format. If we could store the passwords in plaintext, then this will be a trivial problem to solve, but that's not secure. So we will address these questions one by one. Even if it seems very obvious that users repeat their mistake, there had been no study showing such. So we did a study with Amazon Mechanical Turk, where we asked the workers to create a password for a hypothetical email service and then type the same password multiple times over a couple of weeks. So 271 workers participated in our study, and they cumulatively logged in for nearly 9,000 times with median 30 times. Almost 1/3 of those users actually made 2 typos in 2 different login attempts. And half of them repeat their mistakes. So we simulated the idea of adaptive typo tolerance on the data we collected, and we found out that if we allow typos adaptively, that will improve the typo correction, that will provide typo correction to 50% more users than the prior character-based approach. So this is an exciting result, and therefore we move on to the next question, where how do you know that an incorrect submission is indeed a typo and not an attacker's guess, without storing password or typos in the plain text? So we designed TypTop. TypTop does this exactly solve that problem. TypTop works in the following way. So TypTop changes the state of password storage. So in traditional password checker, we store the hash of the password. Here we'll store some extra information. So there will be a cache that stores the legitimate typos that user made in the past. There will be a wait list where that will store the user's incorrect submissions, which are waiting to be approved to be legitimate, and then there will be some auxiliary information. So when a user registers with a password, TypTop generates a pair of secret and public key, encrypts the submitted password using the public key, and encrypt the secret key using the submitted password, and store the public key in the plain text. So this whole thing is a TypTop state, and it will be stored in the persistent storage. I'd like to point out the encryption scheme for to encrypt the secret key using the password uses a password-based key derivation function, which makes encryption and decryption functionalities as slow as any typical normal password hashing. Also, it uses a authenticated encryption so that every time you try to decrypt an entry with a wrong password, the decryption will fail. Now, when a user tries to log in with a password, TypTop will try to decrypt the entries. Sorry for the mess in the font because of different operating system. So TypTop will try to decrypt the entries in the cache using the submitted password. And if the decryption succeeds, it will allow the user to log in. In this case, however, as you can see, the submitted password is wrong, so decryption will fail, and the login will be rejected. In the background, though, TypTop will store the incorrect submission in the waitlist after encrypting it using the public key. Getting the login rejected, the user will eventually submit the correct password, and the decryption of the cache entries will succeed, and the user will be allowed to log in. Also, this decryption will output the secret key that was generated during registration. So now we can decrypt the entries in the waitlist and find out the old incorrect submissions. And now we can check whether or not they're legitimate, because we can also decrypt the auxiliary info to find out the registered password, which is required to make edit distance-like computation. And if we found that any of those incorrect submissions are legitimate, we store it back in the cache using the same way we stored the registered password, that is, encrypting the secret key using this typo. So in future, if user makes the same typo again, one of these cache entries will be successfully decrypted, and the user will be allowed to log in. Notice we achieved adaptive type tolerance, that is, accepting a typo that a user made in the past without ever storing the password or the typos of it in plain text. I glossed over some of the details of TypTop. For example, the cache and the waitlist are of finite size, obviously, and that's why we need a caching policy to insert and evict the typos. For waitlist, we use simply first in, first out policy, but for cache, we tried out some different standard caching techniques, such as least recently used or least frequently used. We devised a new caching policy for what we call probabilistically least frequently used. I will not go into the details of the caching policy, but the idea, I will only note that this PLFU actually benefits security while being very competitive in utility. Also, if you need any extra information, such as the frequency of the typos to enforce the caching policies, we can store them in this auxiliary info. and encrypt it using the public key so that we can find this, we can decrypt it whenever user successfully log in. We don't want to reveal the number of actual entries in the cache or the waitlist. That's why we fill the empty places using random values sampled from the corresponding ciphertexts. We also permute the entries in the cache because it helps in security, as we'll show in the next section of the talk. And finally, we don't insert any typo. We don't allow any typos that matches the edit distance check. We also check whether or not a particular typo is easily guessable. We use like simple password strength meters. We use ZXVPN, but we can use any other password strength meter. But we disallow typos that are easily guessed to get inserted into the cache. With all this, the next obvious question is TypTop secure? So as we evaluate any other password checker, we evaluate TypTop in two most popular threat models. The first one is remote guessing attack or online attack, where an adversary uses the login API of TypTop and try to impersonate a user by guessing their password or a typo that is active in the cache. The analysis of this whole attack is very similar to the one we did in the last paper. And we showed formally and empirically that there is no security loss in this attack. I will not talk more about this paper, this attack. Please look the paper for details. The more interesting attack, which is smash and grab attack, because we stored what is stored in the password storage. Now it will be interesting to see if an attacker steals that data, what it can learn from it. So we'll talk more about this in this talk. So what is smash and grab attack? We assume that the attacker has accidentally has compromised the server that hosts TypTop and still stole all the data that is stored in the persistent storage. Now, the goal of the attacker is to learn the registered password. The obvious thing the attacker can do is just brute force try to guess the registered password, just like he could have done against any other password checker. I mean, we would like to be like this, but there are extra information stored in the cache. An obvious question is, can the attacker do something better than this? Now, we will show over this talk that he cannot. So let's see how. So we show a two-step reduction, showing how the attacker has to guess against the registered password. So you consider an intermediary strategy where an attacker tries to guess the registered password or any typo that is stored in the cache. So first, via cryptographic reduction, we'll show that the attacker who stole the TypTop state won't be able to learn any information from the state unless he can guess either a password or a typo that is active in the cache. And then, after using a combinatorial argument, we'll show that attacking or guessing typos are futile, and the attacker will be better off by trying just to guess the registered password. So let's look at the first part of it. So we claim that the state of TypTop appears completely random to an attacker unless he can guess one of the registered password or a typo of it that are stored in the cache. We show via an indistinguishability game, we show that the attacker cannot distinguish between a real TypTop state and a TypTop state that are filled with random values. Now, if attacker cannot distinguish between these two, obviously the attacker cannot learn any information. Now, these are all assuming that the underlying encryption schemes that we have used, the password-based encryption scheme and the public key encryption schemes, are secure. And they are because we use some well-known, well-analyzed encryption schemes. So the only strategy of attacker is to now try to guess the password or the typo that are in the cache. So this brings us to the middle attacker, the strategy of the middle attacker who tries to decrypt the entries in the cache by guessing one of the password or typo. Now, I would like to remind that this decryption is slow as normal password hashing. And every entry in the cache uses different salt. Therefore, the attacker can check only one entry at a time. Moreover, attacker learns nothing by guessing a password or a typo that is in the cache, but he decrypts a wrong entry in the cache. Finally, you also remember that we randomly permute the entries in the type, randomly permute the entries in the cache. Therefore, every typo has equal probability to be in any location in the cache. All this together seems like trying to guess a password, trying to guess a typo will be really hard. Now, will it be like always very hard and we can just finish the talk here that you cannot do? That's not true. There are some situations, hypothetical situations, where attacker will get benefit by guessing typos. For example, consider a situation where in the universe, every user makes a certain typo fairly often. And therefore, that particular typo will be always in the typo cache of most of the users. And attacker can get significant advantage by guessing that typo. Now, this is an artificial distribution, obviously. But this gives us an intuition behind when guessing a typo will be beneficial. And this leads us to the notion that if we can ensure that there is no such typo exist in our typo distribution, then the attacker has to resort to guess only the real password. And we captured that notion using this criteria we call T sparsity condition, where the T is the number of typos that are allowed in the cache. So in simple words, this says that if in a typo distribution there are no typo that are frequently in the cache of many passwords, then we'll call the distribution T-sparse. Obviously, that's very vague. Mathematically, this is like this. I will decipher the equation in parts shortly. So first, look at this tau w tilde, or what we call cache inclusion probability. So cache inclusion probability is a conditional probability that a particular typo will be in the cache given that the original password is w. This cache inclusion probability depends on how user mistypes their password, that is the typo distribution, and how TypTop caches typos, or that's the TypTop's caching policy. Now let's look at the equation. So we'll call a typo distribution T-sparse under TypTop's caching policy if, for all typo, the following is true. The sum of the cache inclusion probability of a typo across all the passwords is less than the sum of the number of typos allowed in the cache. And we give a theorem stating that if a distribution is T-sparse, then the best strategy of the attacker is to just try to guess the registered password. Let me give you the intuition behind this proof. So if an attacker comes up with a list of guesses against registered password and typos, we can give another attacker, if the distribution is T-sparse, another attacker that comes up with a list of guesses against only the registered password and obtains higher advantage. The remaining question is whether or not real password distribution are T-sparse. So we did some empirical study by modeling typo distribution using the data we collected from Mechanical Turk this year and last year. And we show that real typo distributions are indeed T-sparse under all the TypTop configurations we have considered. This concludes our proof that attacking TypTop state is no easier than attacking a standard normal password checkers. As we just showed, that TypTop provides higher utility and TypTop corrects more typos than prior work, and TypTop is secure against online and offline attacks. So we went on and built one. So we built TypTop as a Unix tool, we engaged TypTop using a password authentication module that is used for Unix password checking. So TypTop will render your computer login Typo-Tolerant. We added an extra logging module to TypTop to collect data about how often users mistype that password or how beneficial is TypTop. Obviously, user can disable login and keep using TypTop. So we installed TypTop in 24 volunteers' laptop. 5 of them use Linux and 19 of them use Mac. The volunteers used TypTop for median 27 days. And from the collected data, we saw that TypTop, the volunteers made more than 500 typos. Now let's see what fraction of typos are corrected by the prior approach, the prior character-based approach, and TypTop. So prior approach corrects 22% of the typos, which is roughly the same as what we saw in the last paper. And TypTop corrects 3 times more. TypTop corrects 63% of all typos that those volunteers made. So to summarize, we designed a system called TypTop that adaptively learns the mistakes that an individual user makes and then corrects a frequent subset of it. We thoroughly analyzed security and showed that TypTop is secure in online and offline setting. And finally, we built a prototype of TypTop that you can go and download and try it out right now by going into typtop.info. So let me conclude my talk by saying that I strongly believe that if we allow small typos while users log in, that might encourage users to adopt better security practices, such as using stronger and longer passwords or locking their computer more often. Though we did not investigate those, that will be like a good future work on these directions. Thanks for your attention, and I'd love to have any questions if you have.
Adam with Eve at the Naval Academy. This is very loud, but also this is very interesting. So I was wondering, there's another place that a lot of typos occur, not just in passwords, but in the username space.
Mm-hmm.
So have you thought about like dealing with username typos? Because actually I feel like when I'm logging into websites, I often mistype my username, not my password. It's like, one, I use a password manager, but also like I often forget what username I am, and so I actually have to manage those as well. And having to recall those is actually sometimes harder than actually having to recall, figure out what my password is, which I can look up more easily. So it seems like a natural next step. So have you thought about that?
I did not, but that's a very interesting point. Yeah, we can look at users, but the challenge is easier because users are in plain text usernames, so we can easily check whether or not they are typo. But yeah, I'm pretty sure there are other big problems that you can address there.
Hi, Ada Lerner, Wellesley College. I haven't thought this through fully because I thought maybe you could answer it more easily. You're talking entirely about authentication here, but one place where I often make mistakes when typing passwords is, say, unlocking an encrypted database or unlocking a password manager or something, where it's not an authentication problem, but actually I'm deriving the key to my database or whatever. And so I was curious whether can this be used in that same sort of context, or does it rely on it being an authentication context where I have someone who's verifying the password?
In theory, yes, you can, obviously, because when you decrypt a database, you use an authenticated encryption, so it will tell when a password is wrong. And whenever there is this situation that you have this option that you can learn whether password is wrong or right, you can use TypTop. Now the problem is if your database has some extra security, just like you have to decrypt the whole thing to be able to tell it's a wrong password and right password, that might be problematic. But yes, very much you can drop in this thing for any password-based authentication or encryption schemes.
Cool, thank you. Great work, great talk.
Thank you.
Hi, Jeremiah Blucky, Purdue University. Great talk. So I was curious about the particular choice of cache size that you used. So I imagine there's a trade-off as you increase cache size, it increases workload for the authentication server. So why did you pick the particular cache size that you used? Can you elaborate?
Yeah, sure. Obviously, you're right that if you have a large cache size, that will have a lot of pressure on the authentication service. The another thing is we want to compare against our prior approach. We use like 5-character functions, and though we never hit the max of this cache size, but I think we can choose something in between 5 or 10 should be fine.
Okay, thanks.
Other questions? All right, let's thank our speaker one more time.